Hey, my name is Luna Silva and this is vector field. A vector field over a plane region R is a function f that assigns a vector f of x and y to each point in R. A vector field over a solid region Q in a space is a function f that assigns a vector f of x, y, and z to each point in Q. We can say that in a plane is 2D and also in a space will be 3D. In other words, a region that is in a space or in a plane, there is a function that will be describe all the situation in the vector field. So for every point of this region, we can assign a f of x and y or a f of x, y, and z vector. We will describe the magnitude and the direction to define how the field in the plane or in a space will behave. Here we have some examples. So we have the gravitational field, we have the velocity field, and we have the electric field. Those are some examples of a vector field. Now we have conservative vector field. We're going to start with a plane, so 2D. A vector field f is called conservative when there exists a differentiable function f, such as that f is equal to the gradient of f. The function f is called the potential function for f. To see if a vector field is conservative, we have to do the test. Let m and n have continuous first partial derivative on and up in this R. The vector field f of x and y is equal to m a hat and n j hat. It is conservative if and only if its first component is a partial with respect to x of some function of x, and its second component is a partial of x, the same function f with respect to y. Here we can make like a little note. So we know that the partial of n with respect to x will be equal to the partial of m with respect to y. And this comes from this. Is equal to m y j hat plus n. Okay. Also, we have to remember that this is in a plane that is 2D, right? So now we have an example that we can start to test. So first we have to see if the function we have is conservative. We have to graph it with the magnitude of 3. And if it's conservative, we have to find the potential function, right? Let's erase this 1 second so I can start over. So we have the same function on top here. So this will be our m and this will be our n, right? So we can start with the partial of m and with respect of y. That is partial of f, that is equal to partial of y and 2x e exponent and plus y x2 exponent y. Okay, perfect. So now we're going in respect to y, so we can put aside 2x and just do the partial 2x exponent of xy, and now here just do the partial of y of x and y. This comes from this. Now we can keep going. So plus, we know that x squared can go on the side and just go and do the partial of y just in y. And now e exponent is gonna stay like that, and now the other way. So partial of y, e exponent, and then the y is gonna stay like that. We're doing distribution here because will be just easier, right? So first the partial of this and then the partial of this. Then we're gonna go and just solve the rest. So 2x exponent of xy. We know that the partial of this will be just x plus x squared, just from here, and just solve the rest, right? So exy will be the same, and here this will just 1, so we don't need to put it anywhere. Plus, so here will be e exponent xy, and then remember, as we did before, I'm gonna make an arrow, as we did before here, we have also to get the partial of x and y, so it will be just x, right? So plus e y exponent of y and x, and then the x and the side, and we cannot forget the y, this y that goes at the end, right? Now here we just need to simplify. That is gonna be 3x squared. I did a mistake. Did I? Oh no, I didn't. I forgot here that we can just simplify this. That is 2x squared because of this and this, right? And then 2x squared, and then just exponent plus 2 squared exponent, right? And x cube exponent, and then y. If you're not sure how I did this bar, so I just distribute, right? So x squared with this, and then x squared with this bar, right? For the reason, got that. Sorry, I erased something. XY. Perfect. So from there we can just simplify more. That will be 3x squared exponent plus e and 3y. Just to let you know that this comes from this part, right? And this comes from this part. So this will be our partial with respect of on y. Now we can do with respect to x, right? So and our x. Okay, perfect. So we have partial with respect to x, right, of 3 cubed exponent and partial with respect to x of 2y. Perfect. So now we can see that here is 0 because there is no x, right? So we can just work in this one. So the partial with respect of x, we can just do the distribution as we did before here. Here in this part, right? We can just distribute and will be x cubed, and our exponent is gonna be the same. And now we're gonna do the partial with respect to x of our exponent, right? And our x cubed is gonna be the same. So we're gonna solve this. That we know that it's gonna be 3x squared, and then the exponent is gonna be the same, and here plus the exponent is gonna be the same. But remember, as we did before, we have to get the partial of this also. So the partial of xy is gonna be just y, because we're taking the partial of x, so it's gonna be y, and our x cube is the same. So this will be our partial with respect to x, and as we see, one second, as we see, this part looks the same as this one, and the other part here looks the same as this one. So our test is done. This is the same. So we can conclude that the vector is conservative. So the vector field is conservative, right? So we'll check the first one. So now that we know that it's conservative, we can just graph it. We have to remember that the magnitude will be 3. So let's go and start. So here we can you see that the magnitude of f, the vector f, is gonna be equal to c is 3, right? So we want to get a unit vector first and then just replace it to 1, right? So let me copy here. Exponent y plus 2y. So this will be the magnitude, and this is how we can graph, right? So in this part also I'll just explain you how we can graph this function. So this is equal to c, and now we know that c is 3, right? So this is gonna be 3, right? So we just kind of simplify the whole function. So here will be 9, because if we pass the square root, will be 2 here, so it will be just 9, right? So we want this to be a unit vector, so we're gonna just divide every in the other part, so it will be the same here. I don't simplify more because it will be just easier for us to replace the numbers that we want to graph and do it from there. Otherwise it's gonna take too long to simplify everything. So this one is gonna be equal to 1, right? So now we can just assign any number we want to graph, right? So this one will be x and y, the number we want, and this one will be what we're gonna graph, the vector, right? So we're gonna just graph some. We're just gonna grab some points, so I already have them here to make it easy for us to graph. So -1, 1, 2, okay, 1 second. And this one. So I'm gonna do the first one here just to explain how I did it, but the rest you can do it from it, right? So we have vector f of the first point, that is 2, 0, right? We're gonna have the whole function here. We can just copy and just paste it here. So this And let me move this. That's for later. So we have that, and now we're just gonna solve and plug in the x and the y and all the spaces we see x and y, right? When you get this, well, we're gonna have this answer, this 4 and 8, right? Because this is a hack and this one is j, right? We're gonna do the same thing with all the vectors. I already did it before, so we're gonna just plug it all this in. But you're gonna do the same steps. Now let me see. Comma -1. Probably there are too many points, but will be good for us to start. 0.8, 4.1, 4.13. Okay. So now that we have this, we can start plugging in some answers. So we're gonna just do the 3 vectors, so it's not too long. We're gonna put here our graph, and we're gonna do like a barrier from the points we have, right? So the first point is 0, is 2, 0, right? And then, no, sorry, is 2, 0, 1 here, 2, and 1, right? This is gonna be like our limit. So our first point is gonna be 4a, right? So remember, we have to remember that our magnitude is 3, right? So 3, and the direction is 8, so we know that it's gonna be this way. 1, 2, 3 here, right? This is our point, our vector 4a. Next vector will be in 0, 1, right? That is 2 is 0 and 2, right? So same thing here, magnitude of 3, and this is 0, 2. Again, next one will be this one, and the direction will be 1, 2, 3 around here. Last one, remember that is 3. Perfect. So this one is going to be -4, -8, and this one is going to be 0, -2. Right? So now we already graph our field and use this 4 vectors. Next in the list, we already did the proof of conservative. We did the proof of we did the graph already, and now if it's conservative, we're gonna find the potential function. Let's do that. Okay, potential function. To find the potential function is gonna be the derivative of m and n. Remember we did it here, m and n. So now the potential function will be f of x and y is equal to the derivative of 2 plus dx. This because of this, right? Dx because dx because this one is in the x axis, right? I did this already and I have the answer here, so it wouldn't take too long. So the answer is this plus there is always a constant when we don't have a limit here. We'll always need to add a constant, right? So our constant will be any function of y, right? We're gonna do the same thing with n. So it's gonna be the derivative of x cubed exponent 2y dy. And this is, it comes from this part, right? So this is equal to, I already have the answer because it will take longer if we explain it here, but this is our answer, right? And always we don't have limits, so we're gonna have a constant that is any function of x, right? This is the same of this, right? And the constant should be the same. So our constant, we're gonna call it k. This part, we're just gonna add it after. So we can say that our potential function is equal to exponent x squared. Now we're gonna add the y squared, and now always adding our constant, right? So let's highlight it so we know this is our y squared and this is our constant, our potential function, right? Here we have now conservative vector fields in 3D space, right? So this is pretty similar as we did before here, as m and n, but now we have a z-axis, right? This is key for us, right? How to know if it's curve, and also we bring this because if a curl of the vector is 0, we can also say that the vector field is conservative, right? In other words, we can also say, we can rewrite this whole equation and say that f will be f of x, y, and z is equal to gradient times, sorry, this is cross product because both are vectors, right? Sorry. Of x, y, and z, right? So this is our curl. And we can see this better as a hat, j hat. Remember that it is just cross products, so it will be probably easy to understand like that. So the partials with respect of x, and then the partial with respect to y, and then the partial with respect to c, and then m and p. See if you see it here, right? So we have m here, we have n here, and we have p here, right? And now if we solve this, it's gonna be equal to this whole thing, right? It's to show you another way to express this whole equation. Another thing we have to add is this is a vector quantity. Vector quantity. Because it's a cross product and we have I hat, j hat, and k hat, right? As we did before, we need to test for the conservative vectors, so it's actually almost the same thing. We need to know that the curl of f of x, y, and z is equal to 0, and also we can add a note that it can say, they can say f x, y, and z is equal to a hat plus n j hat plus p k hat, right? And the partial of p with respect of y should be equal to the partial of n with respect to c. Also, the partial of p should be the partial of p with respect of x should be equal to the partial of m with respect to c in here. Also, the partial of n with respect to x should be equal to the partial of m with respect to y. So this is a note and a key for us to take in mind, right? And this is in space. That will be 3D, right? So just to recall, this is just probably almost the same as we did before here, but with one more variable, right? That it will be these two variables for us are new, right? Now to explain all of this, we have an example. So we need to see if this vector field is conservative, and also if it's conservative, get the potential function. So first, to know if it's conservative, we can just write first the whole function here, right? To have it there better, and just say This one is our M, this one is our N, and this one is our P, right? And now we have the first part. This part number 1. So the curve of a vector of x, y, and z is equal to the gradient of time cross product, of x, y, and z. So this is equal to y, a hat, j hat, and k hat. Remember that is plus, minus, plus. So the first partial with respect to x, partial with respect to y, partial with respect to z, right? And now m, n, and p, that m is going to be here, n here, and p, oh, we're running out of space, okay. Let's do it again. Here. And P will be 3xy squared C 2, right? Yeah. As we know, we can just solve this. So I did it before, so I'm gonna just give you the answer and show you how I did it, right? So the first one, I got it from this and this. That will be our I hack, right? So the next one will be this 6x YC 2 that I got it. That I got it from this one and this one. The partial of C and this one, and also will be a hack, right? So remember to put the a hack there. Now the next one is negative because we're doing j hacks, so remember this one is negative. So for the next one will be negative 3y squared c squared. This I got it from this one and this one, right? The partial with respect to x, and the next one is 3y squared c squared that I got it from the partial with respect of c here and here, and also j hat, right? So let's keep going. Next one, positive, because we're doing let me see what other color here. We're doing k-hack, and so we're gonna do next. So 2yc 3, that will be next one is this one and this one. After this, the last one will be minus 2y c3. This is going to represent this one, and as we know, is k-hack. So k-hack add that. So we're gonna confirm if this is conservative, checking at this part. So the partial of P should be the same as the partial of N. Let's check. Partial of P will be the same. Perfect, yeah. So when we do all of this, we're gonna have a zero vector, right? That is also good for us because now we can say that our function is conservative. So now the second part. So we did this one. The second part is gonna ask us for the potential function. So as we did before in the last problem, the potential function is just gonna be the derivative of our mn and p. So y squared c cubed dx. I'm going to show you we got this from our function at the beginning here, right? I did already this, so this will be equal to x y squared c cubed plus, remember that we don't have a limit, so we need a constant. That the constant is going to be any function of y and c, right? Next will be the derivative of y, the dy, sorry. So it's going to be 2xyc cubed. So dy. And also this, we got it from the function here. I did this already, so this is equal to 2x c cubed y squared over 2. And to simplify this, we're just going to go and cancel this out. And this is going to be equal to x y squared and c cubed, right? Same thing, we need a constant that is going to be any function of x and c. And the last one is going to be f of x, y and c is equal to the derivative of 3xy squared c squared dc. I got this from the function here at the beginning. So the answer will be x y squared c cubed plus any function that is x, any function of x and y, sorry. So now we have to compare, right? So this and this are the same. So these ones are going to be our potential function. All these are our constants. And our constants, we're going to name them k, right? Our k constant. So for our potential function, we got f of x of y and c is equal to x y squared c cubed plus k, right? Because it's our constant, right? So what else? Here we got the conservative and potential function. And now here we finish our vector field lecture. Thank you so much.